All right, well, let's see if we can get through what I want to get through today. And if we can, at the end, I'll ask you, or not ask you, I'll kind of do a summary of the solids of revolution. I know in my morning class I did have quite a few students who are still confused on when you subtract, when you add, how do you find that outer radius and inner radius. So I'll try and come up with some like generic sort of template for you, but it's time permitting, all right? We're gonna actually move on, and we're gonna talk about this topic it's actually in 7.2. At the end of 7.2, we've covered 7.2 with the exception of this, and we actually did 7.3 also, shells. And the reason why I'm coming back to this and doing this now is because this has nothing to do with solids of revolution. All right, so I figured if we did shells still is dealing with solids of revolution. This concept can kind of stand by itself on its own. All right, so there's really not like a technical name for this, but I'll call it something. This is solids with common cross sections. All right. Yeah. Okay. Solids with common cross sections. So let me take something that may be familiar to you. Let's say we take a cylinder and just take half of a cylinder. All right. So there's like half of a cylinder. See it? If I were to come in here and let me show you what this looks like from the top. Okay, from the top it looks just like this, right? Just like a rectangle if I'm looking straight down at this. If I were to come in here and make a cut right here, slice through it, it would be the same as cutting it through there, right? And if I cut that and I took that piece off and I looked at it from the side, what would it look like straight from the side? Like a rainbow. It would look like, you know, a little semicircle, right? Yeah? And no matter where I cut it, if I cut it further back and I took a look at that cross section, it would also be a semicircle, right? And for this particular solid, no matter where I cut it, right, as long as my cut is perpendicular to, let's say, this side, then every single cross section will look like this. So they all have a common cross section of a semicircle. Would you agree? That's kind of what we're going to do here with a slight exception. And that's our cross sections all have to look the same, like they all have to be semicircles, but they don't necessarily have to be the same size. Or maybe when I do a cross section, I don't get semicircles, I get something else. Like,
there was a problem like that in the homework.
Yeah, it's on the homework, and you probably couldn't do it because it was number 38 and 39. Yeah. So what if we had this like shoebox? Wouldn't it look exactly the same from the top as that other one did? But when I do my cross sections and cut, when I take a look, it's going to look like, well, that looks like a rectangle, doesn't it? Right? All the cross sections would be the same. So it doesn't have to be a semicircle. It could be a rectangle, could be a square, could be a triangle, could be a lot of different things. But the idea of this cross section, I'm trying to get that in your head first. Got it? Kind of understand? All right. So let's now take this region that's bounded by these two curves, right? And so we're talking about this region in here. And let's say that that is the base of a solid. Okay, so that's kind of like the ground. And what I want to do is I want to fill above this and create a solid. But here's what I want. I want the solid to be so that when I take cross sections like this and start cutting them, if I were to look at them from the side, they would be squares, but the length of the square, the length of each side, would actually be equal to the distance from the red function to the blue function. So like this. If I do this right here, draw that little, let's do like a little sliver. That look familiar to you? We've done slivers like that in the past, like a little rectangle in there. Imagine that's a little cross section in here. When I look at it from the side, I want it to be a square. I don't like that. I want that to be a square. A little square slice. Does that make sense? So I cut from the top, I take that piece out, I look at it, that's what I see. But see, if I move my rectangle over, what's going to happen? I take that slice, what's it going to look like compared to that one? It's still going to be a square, but it's going to be bigger, isn't it? So I'm going to have a bigger square. That inner piece would be bigger. Something like that. Right? That's what that inner piece. And then what if I take a little slice off of this little rectangle right there? I'm going to have a little smaller little square over here, right? Get it? So the question is, if I were to make a solid that looks exactly like this, where cross sections form squares, with the length of each square being the distance between the two functions, what's the volume of that solid? What is its volume? Well, what we've done in the past when we had problems like this is we tried to come up with a formula, right, for a single one of these, and then we use the integral to add them up, right? So maybe we can generate a formula that would represent the volume of each of these slices. Now I want to show you, I want to use the computer to give you a better picture of what's happening here because I can only do so much on the board. So let's do it. Let's go ahead and lay this thing down on the ground. Okay. Oh, went too far. Okay, that's laying on the ground. Can you kind of see it? Maybe I should. Oh, I'm going to lose it. Okay, that good? Now, let's make some squares. So I'm going to make squares. And when I do that, so you see what's happened is I'm taking the distance from here to here. Actually, it doesn't look very proportional, but it's supposed to go up the same distance, over the same distance, down the same distance. And if I move this to like different slices, then you can see how that square changes shape. See it? Go to the middle, it's the biggest it's going to be. I go towards the other side, I'm going to get very, very small squares until I really get no square at the very end. Now if I put all these together, right, if I put all these together, all these little slivers, then I'm going to get a solid. And that solid, when filled in, would look like this. That would be the shape. And we want to know its volume. Get it? Yeah. I mean, there's some weird shaped buildings. Architects get crazy and they do things like this. Okay? Now, we could do squares. We could also do something else, like let's do those semicircles. So what I'm doing here is that I'm going to come in here. I'm going to say that this right here, this little rectangle on the bottom, right? From that, that's actually the diameter of my semicircle. And I'm going to just create a little semicircle out of this. So I've got something like this. Right? And then I do that. If I go further towards the middle, I'm going to have a larger semicircle, right? And the closer I get to the edges, the smaller the semicircle is going to be. Make sense? That should be a different shape than the one we just looked at, right? And it should have a different volume. Let's go ahead and see it. Now, unfortunately, I was trying to work on my code before I came to class. There's something in here I need to fix for semicircles. It's drawing the full circle, but imagine that it's cut off, like just cut this off at the bottom. Then do you see the half circle up there? Yeah? So as I move this thing around, as I move it through, the circle gets smaller towards the edges and then back towards that edge. So we get this shape right here. Definitely different than the last one, right? What's the volume of that? All right, we could do that. Maybe we could do equilateral triangles. Equilateral triangles are triangles that have all the same side, right? So what if I say I'm going to use this length right here as one length of the equilateral triangle and then form an equilateral triangle right above it and just create that little piece like that. And as I get closer to the edges, the triangles get smaller, move towards the middle, it gets bigger, and we'd have this. So there's my triangle moving through. And if we put them all together, we get this shape. Do you understand the concept, the idea? Yes? Okay, so let's go with squares. We'll start with squares. I'm going to give us a specific example here. This is actually exactly what we're going to be finding the volume of, but I need to state the problem as if it would appear to you, all right? The way it would appear in like a book. So let's do it. Find the volume of the solid whose base is the region bounded by that's like a flyer gnat that's flying around in the up there, but it's showing up on here. Right. Find the volume of the solid whose base is the region bounded by y equals 1 minus x squared and y equals x squared minus 1. And cross sections perpendicular to the x-axis form squares. So this right here, what I'm going to underline, squares, that could change in the problem. We could change that to semicircles, we could change that to circles, we could change that to equilateral triangles. There's a lot of different things it can be. For this particular example, it's going to be squares. So we're going to start first by understanding the region that we're talking about that forms the base, and that's the region bounded by these two. And that's exactly what I just had up on the screen a second ago. So it really doesn't matter which one we color blue and which one we color red. But I'll just do this one. Which of the two functions is that one? This is y equals what? 1 minus x squared. And then the other one is the parabola that opens up. Comes something like this. This one is y equals x squared minus 1. So that's the base of the solid, right? Now, this next part is where we come in and we do that slice. So when we look at it from the top, we're going to slice straight down. So that's going to create our little infinitesimally thin slice. Okay, so we're taking like a deli slice out of a piece of meat, right? And we're just going to slice through it. And the important thing here is that it says cross sections, which is what I'm forming when I do a slice. I'm creating a cross section, right? My cross sections have to be perpendicular to the x-axis. So I could slice it this way, right? I could slice it like this. I could slice it any way I want, right? I could slice it like this. To be clear, we want to make sure you understand that the slices that we're making are perpendicular to the x-axis. Understand? That's why that wording is important. So cross sections perpendicular to the x-axis form squares. So when I slice that and pull it to the side, I should have a square. All right, so let's try and draw this same picture in three-dimensional space. So this might be one of your first experiences trying to draw something 3D like this. So whenever we try and draw 3D, always start with what we call the y-axis, which is just straight up. That usually is a sorry, did I say y-axis? I meant to say z-axis. This is the z-axis. Usually the straight up and down is the y, but what I'm going to do is I'm going to draw now an x. But not like an x that has 90-degree angles. It's going to be like a smashed down x, like this. And if you draw like that, then you get a pretty good idea of depth. Do you kind of see depth there? If you try and draw it like this, with a perfect, like 45-degree, like these are 90, right? That doesn't look three-dimensional, right? Looks like a snowflake or something, right? Yeah? Okay, so scrap that. We don't want that. Now what this is it's a representation of that where your x-axis is here, your y-axis here, and that's like the ground. And then you got the z-axis that's coming up. Do you all see it? Okay, now try and draw your parabolas in there. Now that's kind of tough, so I'm going to mark out like 1 unit this way, 1 unit this way, 1 unit this way, 1 unit this way. And now I'm going to try and draw my parabolas. The blue one is on top, so the blue one should be the one that's going like this, right? So I start here, I need to get to here with this thing that looks kind of parabolic. Then I got to go from here to here in this way, so it's kind of a tighter turn there like that. Do you all kind of see that? Then I'm going to start with my red one. My red one's got to go from here to here, again kind of looking parabolic, and then from here to here, again kind of looking parabolic. So I think that's pretty damn good. What do you think? No? Damn's not a bad word. Hell's not a bad word, and damn's not a bad word. Just listen to the radio. I can get away with a lot of stuff these days. Right? It is. There's not much censored these days. It's hard to drive around with the radio on with my daughter in the car. Okay, you see it? And one of my students in my 9 a.m. class asked me and said, hey, on the test, do I need to draw this? And I said, yeah, why not? And, well, I'm not really good at drawing. I said, well, I wasn't good at drawing either when I was in your shoes, right? When I was in Cal 2, I couldn't draw in three-dimensional space like this. You have to practice. You get better, just like anything else. All right, now let's try and draw that little sliver on the ground, which is going to be, since it runs parallel to the the y-axis, right? That means when I draw it here, it's going to need to run parallel to this axis. So I'm going to draw my little rectangle in here like this. There it is. See it? And now I want to form a square, which means I need to go up, over, and down. Give it a little thickness to it. And there's my cross section. How does yours look? Pretty good? No? I think you need to smash your X down a little more.
I think I need to
Take art class? Okay, so this is an important drawing because what we're trying to get here is really just a formula for this slice, right? We want a formula for that single little slice. If I can figure out what the volume of this little piece is, then all I need to do is do an integral to add them all up. So imagine we're going to move this rectangle from here over, right? We're going to let x go from here to here across. That rectangle is going to change. As I do that, I build these squares up. These squares are going to change shape. So if I can find the volume formula for one of them, I integrate, I get the whole thing. Yeah? So, what is the volume? Well, length times width times height, right? Length times width times height. So we know how wide this thing is. How wide is that? Dx, okay. And do we know this length? Yeah, it's the distance between these two functions, which if you come back over here, was the top one minus the bottom one. So this should be the blue one minus the red one, right? I'm gonna kill that thing when it gets close enough to me. It's flying around, it's bothering me. Okay. All right. So this one minus this one? Yeah? Y'all don't see it up here? No. You see it, right? Okay. All right. So top one minus bottom one. Tell me what that is. 1 minus x squared is the top one, right? Take away the bottom one, which is x squared minus 1. Now let's clean that up because that's just algebra, right? What's 1 minus x squared minus